I can go on then?
Yes, please go on. Yeah.
Okay. Okay, so yesterday we stopped a bit in the middle of this calculation, so we can take it back from here. Basically, you remember I was trying to explain what is the principle of the measurement with the pulsar timing arrays. And so the idea is that one needs to compare two next pulses that the pulsar is emitting at the time difference p. And basically the effect is this shift in time on the arrival time due to the fact that the space-time metric from the pulsar to the Earth is perturbed by the gravitational wave passing by, and especially that this gravitational wave, so this perturbation in the metric is time dependent. Okay, so that's the key aspect here. So we arrived to this formula for the time difference here at Earth, and we did this just a change of variable, assuming, of course, that with respect to this equation here, that Hij has a waveform. Okay, that's why here I write, you know, in this thing, it was generic, a time and length dependence, space dependence. On the other hand, here I'm just saying that the space dependence, the space-time dependence is the one of a plane wave. Okay, so I have t minus k dot r. Okay, and then one can perform this change of variable where now the only difference is the fact that you are considering Hij at the point x plus p minus Hij at x. Okay, and this change of variable also makes this particular factor come out of the integral. Okay, so nothing complicated, you can just do it on your own. But now we said, okay, let's see what we can do with this particular combination, and let's make this hypothesis that the source of this gravitational perturbation here, of these gravitational waves, is the spiral of a supermassive black hole binary. And then we ask, okay, in this case, what is the typical scale of the time variation of the metric perturbation? Okay, and I said that this can be done assuming, the simplest description of a binary system, which is the one in Newtonian gravity, where we have 2-point masses which are orbiting one around the other one, and one can reduce this system to a system in the center of mass of the system of just one object in a circular orbit. I'm sure we will do this in some lecture, or you did it already. So in the end, the frequency of the emitted gravitational waves in this particular case is related to the time to coalescence and to the chirp mass with this simple relation. Okay, so based on this relation, we see here, let's suppose, as we said, that we want to consider the spiral of a supermassive black hole binary, okay, for chirp mass of the order of 10 to the 9 solar masses. And a system which is far away from coalescence. Okay, so the time to coalescence, we fix it to 10 to the 4 years. With this kind of combination, we fall into the nanohertz regime, or 10 to the minus 8 hertz. Okay, so that's exactly the frequency range of detection of pulsar timing arrays. Okay. Now, why? So let's see with this what we can do on this formula. Now it is clear that then the gravitational wave varies on a scale of about 3 years, okay, which is the inverse of this 10 to the minus 8 Hertz. Okay, so that's the typical time variation of HIJ. While P here is the period of the pulsar, which is a millisecond. Okay, so the pulse is emitted each millisecond. So it appears obvious here that this combination of the frequency of the gravitational waves times the period of the pulsar is much, much smaller than 1. And therefore, this quantity can be Taylor expanded. And once one Taylor expands this, because there is this minus Hij, one just remains with the derivative of Hij with respect to x times p. So the integral and the derivative go away, and the final result for this delta t is now this one, in which I have here delta t over p. So I just took the increment here that comes from the Taylor expansion, that is p, and put it at the denominator. This term remains the same, and then I have Hij at this boundary here, which is at Earth, minus Hij at this boundary, which is at the pulsar. Okay. So in the end, this represents the relative change in the rate of the pulses measured on Earth because of the gravitational wave passing by. Okay, so that's exactly our observable. We want to know by how much the time of arrival is perturbed with respect to the interval at the interval between the emission at the pulsar, how much the time of arrival is perturbed due to the gravitational wave. And that's what we found. And it is given then by two terms, one term which is the gravitational wave at Earth, okay, so TE plus L and RO, where RO is the position at Earth, and one term that is the gravitational wave at the pulsar, so T emission, and RE, where RE is the pulsar position. Okay, so the point is that in order to clarify what is often found in the literature, which might be misleading, I want to state, so this is the change in the frequency of the pulses due to the gravitational waves, okay, in the frequency of the pulses, I mean at the receiver, calculated between two successive geodesics, okay, that's what we have done here. And it is not the redshift experienced by a single photon, on the same geodesic, which is the usual gravitational redshift. And this usual gravitational redshift actually depends on h dot. So the point is that these two expressions become the same in the limit of infinitesimal p, because we can do this Taylor expansion. Okay, so in the end, basically the two expressions, in the end you can interpret this as a gravitational redshift, which is what you find written in the literature often, but conceptually it is different. It is not gravitational redshift, it is the comparison between the path of two nearby geodesics in time, okay? But because of this Taylor expansion, in the end, you get practically the same expression as the gravitational redshift of one single geodesic. Okay, so now let's go back to our result and then let's try to find how big it is. And for this, we basically express what is the amplitude of the gravitational wave by this supermassive black hole binary. Okay, and so it goes like 1 over the luminosity distance of the source, that here I have normalized to 1 parsec. Okay, then it goes like the chirp mass to the 5/3, which is now in this particular expression normalized to the solar mass. Okay, so this behavior you find it in, for example, in the Maggior's book. It is the standard one at zeroth order post-Newtonian expansion for a binary emitting gravitational waves. And then it goes like the frequency of the gravitational waves to the 2/3. That is now normalized to 10 to the minus 8 Hertz. And so with this normalization, okay, we see that this is the prefactor here. And therefore, if one puts 10 to the 9 solar masses and the binary at a distance of 100 megaparsec, so some other galaxy at the center of some faraway galaxy, one finds that this particular shift is tiny, okay, of the order of 10 to the minus 16. But as I told you, what is the observable is what is called the timing residuals. Okay, so the timing residuals is the integral of this particular quantity over a given time span. And the time span is basically the observation of no, sorry, in this case, sorry, the time span is the period of the gravitational wave. Sorry. Okay. So let's now integrate this timing residual from some reference time to about 3 years, okay, which is again the inverse of this 10 to the minus 8 Hertz of this particular number here, and one finds 60 nanoseconds. Okay, so this is now the key, really the key reason why it is possible to measure the gravitational waves from supermassive black hole binaries with pulsar timing arrays. Okay, and the reason is that the gravitational wave with a period of a few years, which is exactly what happens, in the emission from a supermassive black hole binary. It emits gravitational wave with a period of a few years. This particular gravitational wave signal induces a timing residual of the order of 100 nanoseconds. Okay, and turns out that this order of 100 nanoseconds, it is exactly the precision of the pulsar monitoring. So that is why it is possible to observe this signal, okay? Because what the gravitational wave induces is equivalent to the precision, or, the precision is actually better than that, of the pulsar monitoring. So that is what makes the measurement possible, okay? And here you see simulated signal. Okay, and this is good. So you see here it is the precision is indeed of the order of 100 nanosecond, and here we have the time, and here we have a period of about 3 years. And so you see how the gravitational wave actually imprints a modulation in the timing residual that is measurable, okay, because it has the right amplitude here with which, you can actually have the precision in the context of this observation. Now, of course, if one observes just for 3 years, it is not enough. One needs to have at least a few years of data, so to see, this, because it is a noisy measurement, to actually see the modulation over at least a few years to be able to infer that it comes from a gravitational wave. And that is why, indeed, pulsar timing arrays have observed for many years, and of the order of 10 or 15 years, and then they have announced the discovery, okay, or the detection. Okay, now this that we have seen up to now is very nice, and it gives you the principle of the measurement. But of course, in reality, life is more difficult because of there are many sources of noises. Okay, so in reality, so the signal from a single pulsar is very noisy. And for now, this is really the analysis of the signal from a single pulsar and in two nearby pulses. Okay. But this signal in reality is very noisy because, of course, the pulses have a varying morphology. Okay, they change in shape, they change in beat in time of arrival. There is some noise on the propagation of the radio pulse due to the dispersion by the interstellar medium. So the radio pulse is spread in frequency, and there are errors due to the time referencing because one needs to somehow coordinate the time on Earth with the time at the pulsar, and therefore one needs to use time standards that are intrinsically have their own source of error, they are intrinsically noisy, and also one needs to know the time at the solar system barycenter. And this is also very complicated to know because one needs to know with extreme precision the position of all and the position and the masses of all the planets. So in reality, what one does to arrive at a measurement is to correlate, once again, as I told you, the same for LIGO Virgo Kagra, which is the cross correlation between different interferometers that are noise dominated in order to get the signal. Here it is equivalent. One needs to correlate between many pulsars to beat down all these noise sources. Of course, some are uncorrelated between different pulsars. Some are correlated. For example, the errors arising from the time standards and the solar system barysensor will be the same for all the pulsar network. Okay, but still, all that it is intrinsic in the pulsar and comes from the dispersion by the interstellar, well, that maybe not, it can be reduced by observing many pulsars. So this, once again, makes you understand how a measurement can be difficult, more difficult with LISA. Okay, so LISA is a signal-dominated experiment. It will have an extremely good sensitivity. On the other hand, it is a single experiment, so this cross correlation is not possible. So there is this trade-off. Okay, so now what happens here when one supposes that one observed this quantity for many pulsars. So of course, in general, the best way to pick up the signal is to observe to focus on the Earth term, okay? Because in the Earth term is always correlated. Okay, is always the same. So because you see the Earth term here, of course, concerns the gravitational wave that left the source at this particular time, okay, which is the retarded time between the time of emission and the Earth. While the pulsar term concerns the gravitational wave that left the source at the time of the pulsar. Okay, so it's the retarded time with respect to the pulsar position. And this term will be different for each pulsar in the network, right? Because they are at different positions. And so this Hij is different, while this Hij here is the one at Earth, and so it is always the same. Okay, so when one does the correlation between many pulsars, the Earth term in general dominates. Okay. However, the pulsar term can create some noise. Okay, unless one can determine the delay of each pulsar, which is difficult. So, in general, with this cross correlation, one picks up the Earth term. And now we will see how. Okay, so let's see now this cross correlation, and this gives then the response of a pair of pulsars. So here, for simplicity, I just put two pulsars, pulsar A and pulsar B, to a stochastic gravitational wave background. Okay, so here I take the timing residual, which is our observable here. Okay, so the timing residual for pulsar A and the timing residual for pulsar B. And I cross correlate them. Okay, so that's the quantity. So we have two time integrals, and we have the residual at time t prime for pulsar A, and the residual at time the shift, sorry, not the residual, the shift at time t prime for pulsar A, and the shift at time t double prime for pulsar B. Okay, and now we can rewrite here this delta T over P by make it explicit this Hij. Okay, so we just do we write it as a plane wave because by the time it reaches the Earth from the supermassive black hole binary, we can approximate this as a plane wave. So it will have the sum of the two polarizations, plus and cross. There is going to be an integral over the wave vector. This is the amplitude for a given wave vector. This is the wave form, okay, where we see, so we take it at T prime, okay, I'm considering this one for pulsar A. And there is here the Earth term that I have collected out. Okay, so here we will have two exponentials. One exponential is at this position, one exponential is at this position. Okay, and therefore one can collect this term here. So this becomes, the Earth term becomes just a 1. And the pulsar terms, we have the rest of the rest here of the difference of the two positions. Okay, so it is LA is the distance between the Earth and pulsar A. Okay, and along UA, which is the vector connecting the pulsar A and the Earth. Okay, and now this factor here is what is usually referred to as the detector response. Okay, is a projection factor that is tells you, you know, with respect to the amplitude of the gravitational wave, how much becomes a signal. Okay, becomes a timing residual depending on the geometry of the situation. Right, and now you imagine that you substitute this thing here into here for pulsar A, and the equivalent one into here for pulsar B. And so now you have this cross correlation that acts on the gravitational wave amplitude. Okay, and therefore you can use the expression for a power spectrum of gravitational waves. Okay, here I wrote it, you know, with eta, but in reality, the time is already here. So sorry, I think this expression is maybe not completely adapted. I should have used the one already Fourier transformed in time that we saw two lectures ago. Okay, but the main point is that there is this delta because of homogeneity and isotropy of the power spectrum. Of course, for this particular situation in which this power spectrum is given by the superposition of the gravitational wave emission of all supermassive black hole binaries in the universe. Okay, the assumption of homogeneity and isotropy is a strong one. Okay, because really depends on how many of these signals are there, and if they really can be considered, or if their signal can really be assumed as homogeneous and isotropic, is a statement that needs to be carefully thought, and we will see this actually in a minute. But for now, let us make this assumption, because the presence of this delta simplifies the calculation a lot. Okay, and then you can introduce it into here, and then another very important observation is that then when you have the product for each delta t over p of these terms, here is where you actually see what I was saying here, that is the Earth term that dominates. Why? Because again, so A is different, sorry. So because again, this particular combination here, which is the wave number times the distance between the pulsar and the Earth, is extremely large. Okay, so we have here that the wave number is of the order of 2 pi times the frequency, and the frequency is of the order of 10 to the minus 8 hertz, as we already saw. Typical distance, for example, 500 parsec. Oh, yeah, sorry. Typical distance of the pulsar. Sorry, this is the typical distance between the Earth and the pulsars, which one can say the pulsar is into the galaxy. Okay, so let's put it to about an order of 500 parsec. And you see, you get that this particular product is of the order of a very big number. So these two terms, they will oscillate like crazy actually, and therefore basically this cross product is just dominated by the Earth term, which is here the one, okay, because I have extracted this particular exponential. Of course, this is true when the two pulsars are different. Okay, otherwise we get a term here if LA is equal to LB, and also if the supermassive black hole binary is not in the pulsar direction. Okay, otherwise this thing goes to 1 and this thing goes to 1. Right. But in the general case in which we have two distinct pulsars, which is the case of interest here because I am cross-correlating two pulsars, and in the most of the cases, we don't have this coincidence of the direction of the emission of the supermassive black hole binary with the direction between the pulsar and the Earth, then we can actually forget about the pulsar term and focus on the Earth term. Okay, and then basically what one does is that one inserts this power spectrum here, one does all the integrals, and one finds in the end that it's possible to rewrite this cross-correlation of the residuals in this form. Okay, so there is going to be just at the end just one integral in frequency, okay, of this quantity. And one can take out a coefficient which depends only on the geometry of the situation. Okay, so the position of the two pulsars, the direction of arrival of the gravitational wave, the polarization tensor of the gravitational waves. And this term can be written simply as a term that depends only on the angle between the two pulsars. And you can demonstrate that it is equal to this quantity. It is not a very easy calculation, okay, but it is possible to do it. And this is what is the famous Ellings and Downs curve. So it is characteristic of a gravitational wave signal, this particular correlation with or dependence on of the correlation with the angle between the two pulsars. It is characteristic of a gravitational wave signal because it is a consequence of the quadrupolar nature of the gravitational waves. And you see it because there are these particular, it has this particular tensor structure. Okay. So, and also this particular sum over the polarizations. Okay, so it is not obvious what I'm showing here. One needs to do the calculation, but you can find it, for example, in the book of Maggiore. And then this particular shape of the signal, of the cross correlation of the residuals with the angle between the pulsars is indeed the smoking gun of the fact that these residuals are induced by a gravitational wave. Okay, so that's what pulsar timing arrays must measure in order to claim detection. Okay, so the observation of the Ellings and Downs curve that, mind you, we have obtained under this assumption of homogeneity and isotropy of the stochastic background. Is a smoking gun evidence of gravitational wave detection. And you can have a look at this paper. It can also be obtained, the same cross correlation, using a single supermassive black hole binary, okay, but averaging over many pulsars. So either one assumes that there is a gravitational power spectrum that is homogeneous and isotropic, and one has a pair of pulsars, but one can also have obtained the same cross correlation, and this is logical, just with one supermassive, one source of gravitational waves and averaging over many pulsars uniformly distributed in the sky. Okay, so because this is just a smoking gun of the fact that one has a gravitational wave signal. Okay, so the point is that, of course, we have many sources of noises, as I said, but for example, the noise that are not beaten down by this correlation, which are typically the noise from the uncertainties on the time standards on Earth and the uncertainties on the solar system barycenter position, do not induce this particular shape of the cross correlation. Okay, so the uncertainty on the time standards on Earth is actually independent on the pulsar angles, clearly. The uncertainty in the solar system barycenter position take the form of a dipole, okay? So not of a quadrupole like this, but they just depend on cosinus theta AP. Okay. On the other hand, one needs to be a bit careful because it is a rotating dipole, okay? And one can have some contamination in the quadrupole because it is a time-dependent dipole. One can have some contamination in the quadrupole from errors on the solar system barycenter. Okay, so the situation is a bit delicate, and indeed it is very important to know the time at the solar system barycenter with enough precision. Okay. So and then now, fair enough. So we have understood, I hope, what is the principle of the pulsar timing array measurement. And now let's focus a bit more on the source. Okay, so as I said that, I have demonstrated that gravitational waves from a supermassive black hole binary have the right frequency to be picked up by these pulsar timing arrays. Okay. Of course, having the right frequency doesn't mean that they are at the origin of the signal. One could have other things with the right frequency that produce the same signal. But because we have many evidence that these supermassive black hole binaries are there, I mean, we have many evidence that supermassive black holes are there at the center of galaxy, then it is reasonable to assume that what pulsar timing arrays have detected is the background from these sources. Okay, so what are these supermassive black hole binaries? They have been observed, supermassive black holes have been observed in the core of galaxies and are the central engine of active galactic nuclei. So this, you see some photos actually of them in the electromagnetic, their electromagnetic emission associated to the matter that is around the supermassive black hole. So a supermassive black hole can originate from the collapse of a massive star or from the collapse of a gas cloud in really at the beginning of the dark ages after recombination in the universe, and then it will grow in mass. It is believed that this initial collapsed objects will grow in mass, or initial collapsed black holes will grow in mass with accretion or mergers, and the mergers in particular are due to the merger of their host galaxies. Okay, but nowadays it's also very fashionable to interpret these as primordial black holes, so their origin could also be primordial. They are observed nowadays to up to very high redshift, and therefore, because they are formed by this collapse of a massive star or a gas cloud, they are then they then accrete matter around their formation, and their presence is really linked to the formation of galaxies and of matter structures in the universe. So, however, all this that I said and this evidence through electromagnetic emission, etc., is evidence for single supermassive black hole binaries or massive black hole binaries at the center of galaxies. Of course, to emit gravitational waves, they must be paired. Okay, and they must be paired not in, not very far away. They must be in a gravitationally bound system, the two black holes that have reached the gravitational wave emitting regime. And this means a separation which is of the order of 10 to the 2 to 10 to the minus 2 to 10 to the minus 3 parsec. Okay, so the two black holes must be close by in order for the binary to lose energy through the emission of gravitational waves mainly, and to produce a strong enough signal and in the right frequency region to be frequency band to be detected with pulsar timing arrays. So we have there is a lot of evidence that galaxies merge, and that after the merger there are what is believed as black holes. Of course, we only observe the matter around them emitting, for example, in the X-ray. There is evidence that the two black holes with their disk go close together. Okay, so we observe the collision of galaxies, and we observe massive black holes at the order of kiloparsec separation. Okay, so these are called dual AGNs. So we know that they arrive close, but not to this particular distance. That is what we need. But then there is friction from all the matter around, and it is believed that this will get the two black holes together to form a gravitational wave bound binary. There can then be also three-body interaction because this boundary is surrounded by stars that can get into the orbit and then be kicked out and then shrink in the binary. And this has been demonstrated that brings the binary at least to parsec separation. Okay, so then there is what is called the last parsec problem. That is, okay, we know how to get the binary to parsec, but how do we get it to the milliparsec? But there as well, there are possible explanations that the bound system again collides with the stars around, or that there is it does have a disk, and then there is a drag from the gas around, from the gas in this disk. So in the end, basically the solution to this last parsec problem, it is possible, but the main point is that pulsar timing array have done this measurement, and therefore it means that supermassive black hole binaries exist and merge in the universe. Okay, when I say that they exist, is also because, of course, here we have a lot of evidence for the presence of black holes. Clearly, a gravitational wave emission is really the smoking gun that these objects are indeed black holes. Okay, so the gravitational wave spectrum from all the supermassive black hole binaries in the universe, in the characteristic strain, gravitational waves, has a red spectrum. Okay, it goes like minus alpha, where alpha is the 2/3. So in a minute we are going to demonstrate this in a very simple setting. The amplitude is actually predicted from all these physics here. Okay, so people do simulations of these objects, of the galaxy evolution, how many of these binaries are there, etc., and they get some prediction for the amplitude. Okay, and in terms of the timing residual power spectrum, this you will see when you open pulsar timing arrays paper that they constrain not directly this alpha, but this gamma, which is the power law of the timing residual power spectrum, which is related to gamma by this equation, and it is 13/3 if alpha is 2/3. Okay, now this alpha 2/3 comes from, can be derived with actually a very simple calculation. Okay, so let us rewrite it in terms of the power spectrum of the gravitational wave energy density. Okay, I think I had some similar relation to this one in the lectures 2 days ago, but this you can find also in the Maggiore's book, etc. So this is the relation between omega and the gravitational wave characteristic strain. Okay, and indeed, if we start with a spectrum for HC that goes like minus 2/3 because of the f squared factor, that gives omega positive slope like 2/3. Okay, so where does this come from? Now, of course, this particular quantity is, if you integrate it over frequency, it gives you the total gravitational wave energy density coming from the superposition of the gravitational wave emission by all supermassive black hole binaries in the universe, normalized to the critical energy density. Okay, and this particular quantity, so integrated energy density, gravitational wave energy density over the emission of all the binaries, of course, is given by the energy density emitted by one supermassive black hole binary, so by a single event, multiplied by the number density of gravitational wave sources, okay, integrated over all possible parameters of this particular function, so this number density, and the parameters are, of course, all time integrated over all time to coalescence, integrated over the co-moving volume of the universe, because you want all supermassive black hole binaries that are there, and integrated over all the possible combinations of the parameters of the binary. Okay, that are many, the parameters of a binary signal, but the most important here is essentially the chirp mass. Okay. Right, so of course this quantity here has nothing to do with the gravitational wave emission. This really comes from an astrophysical model for the binary population. The gravitational wave emission of a single event instead at the source is given by this formula. Okay, so I had it in previous slide as h dot ij times h dot ij. Here I just rewritten ij as plus and cross polarizations, and the product becomes a sum. Okay, so this you can demonstrate is a straightforward calculation. And there is a factor 1 plus z to the 4 gravitational wave emission at the source. Okay. Now, let's now see what is this quantity before we substitute it in here. Okay, so that's once again, the gravitational wave emission by a binary is the same expression that I've used here, okay? Shear mass to the 5/3, frequency to the 2/3, inversely proportional to the luminosity distance. And there you are, okay? So here we are at the binary, so it is not the luminosity distance, it is the coordinate distance at the binary, okay? And Ts is the time at the source. We have a chirp mass to the 5/3. There is an angular factor due to the fact that here I've taken the plus polarization. If it was crossed, this was just a cosinus. Okay, and then we have f to the 2/3 and the phase, and this is h dot, so I need to derive in time f to the 2/3 and the phase that are quantities that are time dependent, okay, for the time at the binary. And now you see our binaries are in circular orbit and with slowly varying radius far away from merger. And so one can consider that the time derivative of the frequency is much smaller than the frequency square. This is a WKB approximation of the system, okay? And therefore here I'm only left with the time derivative acting on the phase, because the one acting on the frequency is subdominant because of this condition. Okay, so because the binary is far into the unspiraling phase. Okay, and then so I write it like this, and then clearly the time derivative of the phase is just the frequency itself. And therefore, in the end, here there is a factor of f to fs, so a frequency at the source, to the 5/3, sorry, to the 5/3. And then when I square it, because here the energy density wants this factor squared, I get this particular expression that depends on the frequency at the source to the 10/3. Okay, so now we are ready to insert this back into this equation with also the cross term. Okay, here is the angular the angular dependence of the plus and the cross term. This is the only difference. All the rest of the factors get out from this sum. Okay, and so we have here the integral on the binary parameters, the integral on the time to coalescence, and the integral on the comoving volume can be rewritten as an integral over all the angle in the sky and an integral over the redshift. Okay, so here I have the integral over the redshift. This factor has remained the same, and then here I get the metric distance, okay, that gets simplified with this factor here, but mind that this is the scale factor at the source. Instead, the metric distance is the scale factor for us at the observer, so there is an extra factor 1 plus z squared that comes about here, but this is not fundamental, okay? There is all this that comes from here. And we drag along, well, that is the important bit, we drag along our chirp mass time Fs to the 10 thirds. Okay. The angular integration over all the sky operates on the angular dependence on the position of the binary that is determined by the two polarizations and just gives a numerical factor. Okay, and then one can express the integral over the time to coalescence in terms of the frequency at the source. Okay, this particular equation comes from, I had it a long time ago, yeah, comes from this. Okay, this relation here, and it is always true for an spiraling binary. And says that dfs over d tau c, so the frequency at the source with the time to coalescence, behaves like the frequency at the source to the 11 thirds. Now I want to bring it here to the frequency at the observer, okay, so there are some extra 1 plus z factors. And now if you combine, so you have you get here from this change of variable an f to the minus 11 thirds, okay, that gets combined with this f to the 10 thirds and makes a minus 1/3, and then you want to write it per logarithmic unit of frequency and you get a 2/3. Okay, and then you say this is the total energy is the integral in df over f of omega, and therefore what you find in the end is that omega as a function of frequency goes like f to the 2/3 over some reference frequency, and the amplitude is determined by all these things here, which is basically determined, these are all cosmological factors, by the characteristic of the population. Okay, so this thing that is modeled out of astrophysical modeling of the population of these sources. Okay, so you see that it is pretty trivial, this particular dependence of the spectrum and this that pulsar timing array must observe in order to claim the fact that what they observe black hole binaries in reality, the fact that these are supermassive black hole binaries on the amplitude and the f to the 2/3 only come from the fact that they are sources emitting gravitational waves far in the spiral, far into the spiral. Okay, now so what does so how correct is this, and what does the measurement say? Of course, so as we've seen, the features of this power spectrum from supermassive black hole binaries, so its amplitude and slope mainly depend on the population characteristics. Okay, and so on this, everything is hidden in this factor here, and there is the binary merger rate its dependence with mass and redshift, the surrounding stellar density, the initial binary eccentricity, because all this calculation has been done with circular binary, okay, but the binary can have some eccentricity, in which case the waveform changes. It has different different relations here, for example. Okay, so and all these can actually change in reality this simple prediction of a spectrum that goes like f to the 2/3 in omega. Okay, so here you see in this picture, which is taken from this very nice publication, the strain as a function of frequency, and you have the vanilla prediction, some amplitude determined by the population and f to the minus 2/3, okay, in h. And then you see how different factors can actually influence this spectrum and make it very different from what this vanilla expectation or prediction is. Okay, so first of all, as I said, the assumption of homogeneity and isotropy of this background is not justified at high frequency. And these are all the spikes that you see here. These colored line, like these, come from actual simulations of the gravitational wave emission from a simulated population of binaries. Okay, and at high frequency, the supermassive black hole binaries are less numerous, right? Because at high frequency, it means that they have gone closer together, and it means therefore that the binary is in a later stage after formation, and so it takes longer to get to this stage. So the binary must have been formed earlier in the history of the universe, okay? So they are less numerous. Most of them will be in the far spiral phase. So at high frequency, then this slope is typically steeper, and we have this discreteness that starts to appear. Okay, the spikes are just the emission from the loudest single source. So we see that the homogeneity and isotropy of the signal starts to break down, and we start to see the effect of the emission by single sources. Then, of course, there is the fact that the binary are not isolated, but they can interact with the environment and have disk or stars coming by, and this makes the hardening stronger, okay? And this can suppress then the power at low frequency, because it means that the binaries are closer together than what you get by this simple assumption of, binaries far in the circular in the spiral phase. And then we have the fact of eccentricity that also enhances gravitational wave emission at higher frequency. Here you can see it in the book of Maggiore, for example. It has a section dedicated to the gravitational wave emission of an eccentric binary. Okay, so in reality, you see here that the signal can look like in reality can be very different from this simple f to the 2/3 prediction. Yet, in 2020, Nanograph, then followed by the European Pulsar Timing Array and the Parkes, so Australian Pulsar Timing Array, have announced the presence of a common red noise in their data, so 12.5 years data. So that's what I was saying before. In order to be able to see something, you need to wait for a longer time scale than just the period of the binary, okay, to get many periods and have your signal. And this is what they have fit. You see, these are their data back then, and this is gamma, so these 13 thirds, and they sort of can see something compatible with this at low frequency. So this was in 2020, and then last year, or no, it's now 2 years ago, I think, because yes, it was 2023. Yeah, 2023. Pulsar timing arrays collaborations, Nanograv, EPTA, Chinese, Parks, the Indian that shares the data with the European one, have confirmed the observation not only of this common red noise, which it is a detection but does not have in itself the smoking gun of the gravitational wave, but they have also shown the evidence for Ehlers-Danlos correlation. So this is really the main announcement. Here we see the case of the European pulsar timing arrays, in which they have two data sets, a very long one and a shorter one, which is the most precise. Okay, and they have a gamma that is a bit shallower than what expected, okay, though the 13th Hertz is within I think this is 5 sigma region. The blue, so the old data set shows a better gamma but less evidence for the Ehlers-Danlos, so I think this can be discarded. So this is the EPTA result. Here you see the nanogravs result. They have a stronger bias factor for the presence of this signal. Okay, and here you see the Ehlers-Danlos detection fixing gamma to 13 thirds or varying gamma. These are the data, okay, and this is the 13 thirds that is sort of expected, though, I mean, with all the caveats that I have explained. Okay, and then there is also a paper that has come out from the International Pulsar Timing Collaboration that nicely shows that all detections are consistent with each other. Okay, so for all the data set, for all the collaborations, the slopes are shallower than the 13 thirds that is expected. Okay, but as I demonstrated, the model is probably not fully adapted. Okay, one maybe should take into account, these eccentric binaries, strong interaction with the environment, etc. In any case, the amplitude and both the amplitude and the slope are broadly consistent with the one from a supermassive black hole binary gravitational wave spectrum. Okay, and all data sets are consistent within 1 sigma. So what I think is in any case of interest for us is the fact that the signal could also be of primordial origin. Okay, so now after I have done this overview of the detection of pulsar timing arrays and the explanation of their signal, the astrophysical explanation of their signal, let me now switch gear and go to, what are the possible sources, etc., of gravitational wave signals from the early universe. Okay, I will not specify now. I will not be specific to the case of pulsar timing arrays. I will start with a broad overview of signals from the early universe. And I think it's a good moment to take questions, if there are.
So in the particular amplitude curve which you showed for supermassive black hole stochastic background, you said that because of not homogeneity not being there, or isotropy, or some high frequency disturbances can be there, and also in the lower side there could be some interactions which can affect. So I was wondering that, do you assume all the supermassive black holes to be clean system without having any matter around, or will the presence of any environment or the matter around them can also affect this?
Yeah, indeed, precisely. So you see all this derivation that I did, um, you know, first of all, is valid for a circular binary, and it is for a circular isolated binary. So it is the superposition of the emission, gravitational wave emission from a bunch of isolated circular binaries in the inspiraling phase. Okay, so this f to the 2/3 is a prediction within this setting. So obviously one needs to somehow make this better or more realistic. Okay, and when you make it more realistic, you observe that yes, it's okay to assume that it is f to the minus 2/3 at low frequency if most of the binaries are circular, but certainly at high frequency there are changes. Okay, so to derive this, I was in this very narrow set of assumptions, but you know, to make it differently, then one needs much more refined techniques, and I am not working on this, right? These people do simulations of the binary assembly of their environment, etc.
Thank you.
Yeah, hello. I had a small question. So you mentioned that this is like a inspiral binary population, and from there we are picking up the SGBW, like massive one. So I'm saying that you already talked about the eccentricity effect. So I am asking about the inclination angle. Is it because like they are averaging out all the inclination angle, that's why it is not matter, or like the inclination angle overall doesn't matter because there should be some susceptibility over the inclination angle also, right?
Yeah, the inclination angle doesn't matter much. It gives you a factor, a numerical factor.
No, but
Okay, so
the total average in the one also there also it doesn't matter. Like, oh, okay. So it is like assuming that all the inclination angles are like uniformly distributed, like.
yes.
Thank you.
I suppose so. So here, basically, what you do is that you take this is the dependence. So the inclination angle or only, enters for each event in this quantity. So this is how the plus and the cross polarization depend on the inclination angle for one binary. So theta is going to be the inclination angle for one binary. And then you want to somehow average this uniformly, as you said, assuming that it is uniformly distributed over all the sky. I don't think this is a far-fetched assumption. So the inclination angle of the binary, there is no reason why there should be a characteristic inclination angle of the population, I think, with respect to us, because we are no special observer, you see. So I think this is pretty good. Of all the assumptions here, I think this is pretty good. Eccentricity is completely different than this. It has nothing to do with the inclination angle.
Hello, ma'am. So I have a question. You said that that GW, it also can come from primordial origin. So my question is there any way to uniquely distinguish between those GW that it is from primordial origin or star collapse?
Yeah, you mean black holes?
Yes, black holes. So
Black
is
holes,
there
yeah.
any way to distinguish them using GW observations?
Yeah, you see, I don't work on that, so I'm sure there are ways now.
Perhaps I could add a word. So if you detect many binary black holes at very high redshifts, well before the star formation, that would be a sign of them being primordial black holes because stars have not formed them.
Yeah, but
It's very hard to, it's very hard to distinguish,
yeah,
Once
it's
they're
very
from a
hard to
black hole,
detect
they're
them,
just
right?
happening.
If they are at redshift larger than whatever, 15, okay, maybe with Lisa. But yeah, I'm not. You see, you need them to accrete enough. Yeah, I'm not sure. So what we will see, but this is a bit of a far away connection, is the fact that, if, in order to produce these primordial black holes, you need to enhance scalar perturbation, the amplitude of scalar perturbations during inflation, so that when the scalar perturbation re-enter the horizon, they collapse. They are of order 1 and they collapse to a black hole. And one can demonstrate that this enhanced scalar perturbation produce at second order a gravitational wave signal that can be detected. So if we detect a gravitational wave background coming from enhanced second order scalars, then we know that most probably there is associated a population of primordial black holes. And then whether these primordial black holes have the right characteristics to form supermassive black hole binaries down to the redshift at which they are observed, it's another question, but it is at least a hint that there are primordial black holes. To observe them directly at extremely high redshift, I mean, for sure it will be a smoking gun. I fully agree with you. I'm not sure it is feasible with detectors. Maybe with the Einstein telescope.
Thank you, Chiara. I don't see any further questions, so you may continue.
Okay. Okay, so now let's see gravitational wave sources from the early universe. Okay, so here we have this cartoon that represents the history of the universe. And as I already said in the very first lecture, here what is extremely interesting is the fact that gravitational waves bring direct information from very early stages of the universe evolution, to which we have no direct access through electromagnetic radiation. Okay, so they bear with them an amazing discovery potential. It's just a potential because you need to have signals. Okay. And in particular, here I've highlighted the time of Big Bang nucleosynthesis, right, and which sort of separates the part of tested cosmology with untested cosmology. Of course, we have tested inflation through CMB anisotropies, but all these energies here of, the early radiation-dominated phase are so far untested. Okay, so now the point is that we also have another frontier here, which is the TeV, which is the frontier between tested physics and new physics. Okay, so this means that basically all the gravitational wave signals, so all the gravitational waves production mechanisms are rooted in at high energy scale when at energy scales that have not been tested yet. Okay, so the predictions of the gravitational wave signal rely on untested phenomena. So it is not clear that these signals are there. It depends very much on the modeling. And therefore, there is a huge parameter dependence, a huge variety of hypotheses, of proposed generation mechanisms, a huge variety of levels of the signal, of spectral shape, etc. And furthermore, these signals are often difficult to estimate because they rely on new physics. So you need to build a model of something that you actually don't know much. And often, you are dealing with nonlinear dynamics, you are dealing with strongly coupled theories, so the predictions must rely on modeling assumptions. Okay. Many actually, so what do we have at hand, at least of which we are fairly sure at these high energies that can generate gravitational waves? Well, these are typically phase transitions, okay, in the early universe, and this means that there is some field in the universe that changes from one state to another. Okay, that because due to the expansion of the universe and the decrease in the subsequent decrease in the temperature, one state has become more energetically favorable, okay, than the other. And so typically these phase transitions that we expect can bring with them non-linear interaction phenomena, etc., that can be strong enough to produce gravitational waves. Okay, because I remind you that to get gravitational waves, there is always in the middle this coupling factor, which is G, right, which is very weak. And therefore, in general, one needs a very high energy in the source to produce a signal that is or might be detectable. Okay, so let's see which phase transitions we can have in the early universe. So the first one, of course, is inflation, which is also can be seen as a phase transition in the sense that the inflaton field goes from a state of vacuum energy domination to a state in which it relaxes into a minimum. Okay, we can have phase transition related to the grand unification theories, okay, in which one unifies all the standard model interactions. And so this of course is a completely unknown process, how it occurs, but in this case the phase transition would be related to the breaking of the symmetries of the high energy theory that describes the universe at this gut scale. And therefore, to be able to get an observational signal from something like this would be absolutely amazing in terms of how much knowledge it would bring us for the fundamental theory describing the universe at high energies. Okay, and this is at an energy scale which is comparable to the one of inflation, 10 to the 16 GeV or so. Inflation can happen also at lower scale. For now, we only have an upper bound on the energy scale of inflation. Proceeding down in energy, one might encounter the Pachequin phase transition that, is a model that has been proposed now many years ago to solve the strong CP problem. Okay, and this is observationally bound to 10 to the 7 to 10 to the 11 GeV. Okay, so this is something, I list this because it's something, of course, we are not at all sure that it happened, but, it is can be seen as a motivated, notable phase, energy phase in the history of the universe, because one has it's motivated from a problem in the standard model of particle physics. We then have, and this we know must have happened, the electronic phase transition, okay, which is the phase transition of the X fields that gave masses to the W and Z bosons. And then another, and this is the frontier indeed between tested physics at colliders and new physics, okay, this energy scale of a bit further than the 150 GeV, so that the TeV scale. Okay, and then further down in energy, we have the QCD phase transition, which is the confinement of quarks into hadrons. So this is now far into the region of tested physics. So one might say, but this we have under control. Yes and no, because of course we are dealing with a strongly coupled theory, and so it's not easy to make predictions. Okay, so this is a bit of somehow a landscape of processes. Of course, there are many others. Here I have sort of given you those that, in my opinion, or to my taste, are motivated also within the standard model, okay? So motivated by what we already know, being the standard model of particle physics or the standard model of cosmology, what we already know, we know there must be something there, okay? So maybe the gut is not fully there, but I mean, does not fully enter into this description, but that's what I believe is one could say about the situation in the early universe with a more or less level of certainty. Okay, but of course in the literature one can find a wide variety of proposals related to these stages and not. So there is a lot going on concerning gravitational wave production at inflation. So first of all, there is the irreducible background from inflation that is due simply to the amplification of vacuum quantum fluctuations of the metric. Okay, so this is the standard case, but as I previously mentioned, there is another sure generation mechanism, which is the fact that gravitational waves can be generated at second order in cosmological perturbation theory by scalar perturbations. Of course, if we stick to scalar perturbation of the order of 10 to the minus 5, second order is 10 to the minus 10, and this is too small to be observable. But if for some reason scalar perturbations are enhanced, then we can have observable gravitational waves generated at second order. One can also go beyond this irreducible background from inflation and introduce the presence of couplings of the inflaton, for example, to scalar or to gauge fields. And in this case, if you break through the coupling to the inflaton, you break, for example, conformal invariance of a gauge field, you can have particle production driven by the exponential expansion of the background. Okay, and this particle production, so you first generate, because of the coupling with the background through the inflaton, you first produce particles, for example, gauge fields, and then they produce gravitational waves. This can also be spectator fields. And then you can have, no, this I already said, so second order tensor in connection with the primordial black holes. Of course, because if you have these enhanced scalar perturbations, then one needs then to somehow go beyond the vanilla slow roll inflationary model. But if you have this enhanced scalar perturbation, then in general you have associated to this the production or the collapse of primordial black holes. One can then, there is a lot of literature about, breaking some symmetries during inflation, so have a space-dependent inflaton or assume that the graviton is massive during inflation and then it becomes massless once inflation is broken, is ended. And one can also have consider the possibility that the gravitational interaction is modified during inflation. So one can have in the same context, a massive gravitational wave, massive graviton that won't propagate at the speed of light, etc. So all this then generates characteristic gravitational wave signal that are different from the irreducible one. Okay, then one has all that can happen at the end of inflation, and these are connected to the reheating. So at the end of inflation, one expects that the energy, vacuum energy that was contained in the inflaton is transferred to particles, probably standard model particles, at least at some point standard model particles, to put the universe in a thermal state. Okay, and this particular reheating phenomenon can happen in very many different models. Okay, and many of those can produce gravitational waves if there are strong fluctuations of some even scalar field. So one can have parametric amplification of a boson or a fermion field coupled to the inflaton that is oscillating at the bottom of its potential. One can have some symmetry breaking associated to hybrid inflation, in which case this can give peculiar feature in reheating. Decay of flat direction as well. So if you have many fields that have a flat potential, but that at some point start to be dynamical when their mass becomes comparable to the Hubble scale. One can have strange configurations called oscillons, etc. And then far into the thermal phase, one can have first order phase transitions. And in this case, because if a phase transition driven by for example, the temperature decrease is a crossover or second order, then it occurs basically without breaking thermal equilibrium, and one doesn't have production of gravitational waves. But if it is first order, then one expects the nucleation of bubbles. We see this in more detail, and so one can have gravitational wave production from bubble collision, from bulk fluid motion associated to the expansion and collision of the bubbles, and possibly from the generation of magnetohydrodynamic turbulence, also in this connected to the presence of the bubbles. And then one can have topological defects, okay, because this kind of phase transitions are probably not the electroweak one or the QCD one, though it's not completely sure, but the GAT scale phase transitions or whatever can generate, be of such a nature that they left over some topological defects like cosmic strings or domain walls. And then these are, these perturb the metric and do generate gravitational waves, either just because of the network of topological defect, or because of, in the case of cosmic string, they form loops that then shrink mainly due to the gravitational production, etc. So these are all, we see examples, but I wanted to give this summary. I'm not sure whether it is complete. No, I would say I'm sure it is not complete. Of all, of all the gravitational production mechanisms that has been put forward in the early universe, but I hope it gives a fairly a fair idea of what we can invoke, let's say, to have at least observable gravitational wave signals from the early universe. Okay, and I will stop here. If there are questions.
Other questions?
So I had just question with the first point itself, the source by second order scalar perturbation. So the formula we have derived, that is the first order and taking the average over the background. So for the second order scalar perturbation, if one includes, so could you tell me that what are the things which, I mean, the scalar perturbation Hij also has to be first order, or one has to take the Hij second order also?
No, it's the scalar that is second order.
But in the
will
Einstein's
see-
equation, we are keeping the second order also. So the Hij second order would also
No. The Einstein equation, so the left-hand side remains first order.
Okay.
The right-hand side, which is the source, is due to second order scalar perturbations. So there you have terms that are quadratic in the Bardeen potentials, okay, at the level of the source. But the left-hand side of Einstein equation, where you actually produce Hij, this remains linear in Hij.
Okay. So you are checking that how delta Tij would depend on the capital phi or capital psi, like the gauge invariant quantities. Second order.
Indeed, exactly. It will be quadratic in capital phi and psi. Mhm.
Thank you very much.
I do not see any further questions. Chiara, are you planning to continue tomorrow, or this is the last one?
I have material to continue tomorrow.
very good.
Maybe not for an hour and a half, but at
Yes.
least for yeah. But it's up to you. If
Absolutely. Yes. Yeah. Just want to
okay.
make sure that, yeah.
Okay.
Okay. So thank you very much, and we will continue tomorrow.
Okay.
Thank you. Bye-bye.
Thank you. Bye bye.